Hello everyone, I am Dr. Sunita Dol. The topic covered is storage organization and allocation strategies. In this video, we are going to cover organization of storage such as subdivision of runtime memory, activation records, compile time layout of local data, and allocation strategies such as static allocation. Learning outcome. At the end of the session, students will be able to demonstrate the storage organization and storage allocation strategies such as static allocation strategy. In the organization of runtime storage, we are going to cover the subtopics such as subdivision of runtime memory, activation record, compile time layout of local data. Suppose that a compiler obtains a block storage from operating system for compiled program to run in. The runtime storage might be subdivided into target code, data objects, stack to keep track of procedure activation, and heap to keep all other information. The size of generated target code is fixed at compile time, so the compiler can place it in a statically determined area. The size of some of the data object may also be known at compile time, so the compiler can place it in the statically determined area. One reason for statically allocating as many data objects as possible is that the addresses of these objects can be compiled into the target code. All data objects in the Fortran can be allocated statically. The stack is used to store procedure activation and the status of the machine just before calling a procedure so that the status can be restored when the called procedure returns. Implementation of language such as Pascal and C use extension of control stack to manage activation of procedure. When a call occurs, execution of an activation is interrupted and the information about the status of machine such as the value of program counter, machine register, etc. is saved on the stack. When the control returns from the call, then this activation can be restarted after restoring the value of relevant register and setting the program counter to the point immediately after the call. Data objects whose lifetimes are contained in that of activation can be allocated on the stack along with the other information associated with the activation. The heap store data allocated under the program control. The implementation of languages in which the lifetime of an activation cannot be represented by an activation tree might use the heap to keep information about the activations. The size of stack and heap can change as the program executes, where they can grow towards each other as needed. Pascal and C both need a runtime stack and heap, but not all languages do. By convention, stack grows down, that is the top of the stack is drawn towards the bottom of the page. Since memory addresses increases as we go down, downward growing means towards higher addresses. Activation record. Information needed by a single execution of a procedure is managed using contiguous block of storage called an activation record or frame. It consists of collection of fields as shown in figure 2. All languages or all compilers do not use all of these fields. Often register can take the place of one or more of them. For language like C and Pascal, it is customary to push the activation record of an procedure on runtime stack when the procedure is called and to pop the activation record of the stack when the control returns to the caller. Now consider the purpose of each field. Temporaries. Temporary values such as those arising in the evaluation of expression are stored in the field for temporaries. Second field, local data. The field for local data holds the data that is local to an execution of procedure. Saved machine status. The field for saved machine status holds information about the state of machine just before the procedure is called. This information includes the value of program counter and machine register that have to be restored when the control returns from the procedure. Access link. The optional access link is used to refer to non-local data held in other activation record. For a language like Fortran, access links are not needed as non-local data is kept in fixed place. Access link or the related display mechanism are needed for Pascal language. Control link. The optional control link points to the activation record of caller. Actual parameter. The field for actual parameter is used by calling procedure to supply parameters to the called procedure. We show space for parameter in the activation record, but in practice, parameters are often passed in the machine register for greater efficiency. Return value. The field for the return value is used by the call procedure to return a value to the calling procedure. Again, in practice, this value is often returned in a register for greater efficiency. Compile time layout of local data. Runtime storage comes in the block of contiguous bytes. Usually, the byte is the smallest addressable unit of storage. The amount of storage needed for a name is determined from its type, and elementary data types such as character, integer and real can usually stored in the integral number of bytes. The storage for an aggregate such as an array or record must be large enough to hold all its components. The field for local data is laid out. The declaration in a procedure are examined at compile time. Variable data length is kept outside this field. We keep a count of memory allocation that have been allocated for previous declaration. From the count, we determine the relative address of storage for a local with respect to some position such as the beginning of the activation record. The relative address or offset is the difference between the address of position and the data objects. The storage layout for data object is strongly influenced by the addressing constraint of the target machine. For example, instructions to add integer may expect integer to be aligned, that is, placed at certain position in the memory such as an address divisible by 4. An array of 10 characters need only enough bytes to hold 10 characters. Compiler may allocate 12 bytes, leaving 2 bytes unused. Space left unused due to the alignment consideration is called padding. When the space is at premium, a compiler may pack data so that no padding is left. The table on this slide shows the data layout used by C compiler. C provides for 3 sizes of integer declared using keyword short, int and long. Compiler allocates 16, 32 and 32 bits for 3 sizes of integers. Storage allocation strategies. A different storage allocation strategy is used in each of the 3 data areas in the organization of figure 1. First one is static allocation. This layout storage at compile time for all data objects. Stack allocation manages the runtime storage as a stack. Heap allocation allocate and deallocate storage as needed at runtime from a data area known as heap. These allocation strategies are applied to the activation record. Static allocation. In the static allocation, names are bound to storage as the program is compiled, so there is no need for a runtime support package. Since the bindings do not change at runtime, every time a procedure is activated, its name are bound to the same storage location. This property allows the value of local names to be retained across the activation of a procedure. That is, when a control returns to a procedure, the value of the locals are the same as they were when the control left the last time. From the type of a name, compiler determines the amount of storage to set aside for that name. Address of a storage consists of an offset from the end of the activation record for procedure. The compiler must decide where the activation record go relative to the target code and to one another. Once this decision is made, the position of each activation record and hence of the storage for each in the record is fixed. All addresses can be filled at compile time at which the target code can find the data it operates on. Similarly, the addresses at which the information is to be saved when a procedure call occurs are also known at compile time. Some limitations are the size of all data objects and constraint on its position in the memory must be known at compile time. Recursive procedures are restricted because all activation of a procedure use the same bindings for local name. Data structure cannot be created dynamically since there is no mechanism for storage allocation at runtime. Till now, storage organization and storage allocation strategies such as the static allocation is covered. Now pause this video and reflect on this question for a minute or 2 minutes and write your response. Once you return the answer to this question, then you can restart playing this video. The question is, which of the following allocation strategy works at compile time? Option A, stack allocation, B, static allocation, C, heap allocation, and D, none of above. I hope all of you have completed this activity. The answer is static allocation because the static allocation lays out storage at compile time for all data objects, and stack and the heap allocation works at runtime. This is the reference used while preparing this presentation. Thank you.